Okay, what we're going to do is we'll go through the material that's maybe a little bit not so necessary for you guys now. We'll come back to it later. I'll skip through quickly. If you've got any particular bits with the homework that's coming up that you're finding a little bit challenging, I'm happy to take questions. Yeah, happy to take questions. If like in the break, when we stop at about an hour, if you've got particular questions you want me to focus on, please come and tell me. We can go through them in a bit of detail so I can help with particular things. If not, I can just roughly guide you. Just as a rough show of handsy type level, I assume you've all started the homework, right? Which question, if I go 1, 2, 3, 4, 5, 6, which ones are the ones that are worst or you want more help with? So is 1 fine? Or 1's easy? 2? Kinda? Haven't done it. You don't get an opinion then. Okay, 3? So doing the numerical differences. That one's fine, not fine. Okay, I'll go through that, definitely. 4. Seeing blank faces. Yep, so 4, 5, 6, 3, 4, 5, 6, I'm getting the impression that you want help with. Okay, that's cool. So getting up to the right point in the lecture so that I can actually help you is a little bit tricky. So compressed schedule, we'll go on to that bit today. So back to where we were last week with me. So it's gone very quickly. So last time we went through numerical derivatives, talked about floating point stuff. You'd have got an impression of the things that can go wrong with floating point. It's really like, this fuzzy thing that below a certain level, I've seen some of you on PRs are asking questions about, like, it's gone below floating point error. I'm getting, like, when I take log, I'm getting minus infinity for one of the plots. It's like, yeah, it's like below this floating point error, you can't really tell what the answer is. So that's sort of a hint for with the plotting on question 3. If you're having problems, it's like anything below the floating point error, don't even worry about reporting it. It's just like, it's below floating point error. I can't actually tell anymore. Cool. So how floating point issues arise. Had a quick little demo of a couple of things that can happen. This really comes in when you're evaluating numerical derivatives. So this is an example of this where there's this, if you take a forward difference approximation, so you take a little step forward in the function, you look at current value, you do a linearization, go, this is the local slope. Because those are, really close together, but big numbers, the relative error it's really bad for relative errors. So when you're trying to interpret for question 3, this is where the problems come from. It's like, if you're over on this side, floating point errors dominate. Over on the other side is where maths is the problem. And, this is a terrible approximation to a derivative. The step is getting too big. So you expect that there's some minimum between these two bounds. So I did write a little thing while I was waiting. See if it stayed here. So you guys have to do the imaginary step method. I think that's the name. I've heard of this one before. I've never actually done it myself. So it's sort of cool you guys get to do it for a demo. The big problem, if you look at, got 2 windows open, that's really annoying. The big problem with this one, when you're worrying about floating point errors, is there's this difference between 2 relatively large numbers. So 2 normal sized numbers, they're really close together when h is small. Get this thing called catastrophic cancellation and all the precision drops away. So if you can do a derivative without worrying about having this subtraction, that's where this little trick comes from. Basically, there's only one trick in applied maths. It's like take a Taylor series and truncate it. It's an interesting idea of projecting into the imaginary numbers. I think this has been described as like a poor man's automatic differentiation. And it's sort of the same idea that, a little bit different. It's like, you don't want to have this subtraction in there. So we're going to go off the real line into the imaginary and we're going to perturb on the imaginary axis. And if we take a Taylor series around that, you're going to get something like f of x plus I, h. So I is the imaginary number, h is this small step, f dashed x, then you're going to get this higher order term. Because it's an imaginary number, when you square it, you get a minus. So you get this f of x, IH times the derivative of f of x minus h squared, blah, 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 plus some higher order terms. Now, when h is getting small, So like 10 to the minus 8, square that, you're like 10 to the minus 16, you're down at floating point already. So if you, without getting so small that you're worrying about floating point stuff, you'll start to get this cancelling out, and it turns out to be a reasonable approximation. This is kind of, I talked really briefly about automatic differentiation. This is kind of the same idea, that you have this squared term gets really small when you apply these rules. So if you look at that, just to the first two terms, this guy's going to cancel off because it's tiny. It's approximately like this. And if you only look at the imaginary part, it's f of x plus IH, and you rearrange that. So there's no subtraction in this. You just have to have a function where you can pass through a complex number. And if you can deal with the real and imaginary parts, you just take the imaginary part. That's what's going on here. And there's no cancellation in this guy. You just have to cut off the imaginary bit, the real bit, chuck the real bit in the bin, and this will end up being a reasonable approximation. So kind of what you expect to see is that the floating point side should go away. I don't know if you've seen this when you've gone through the example of doing this this type of approximation for the derivative, that you'll see this guy coming down, and what you would expect at some point is the error gets really just sort of tiny and constant and small. You don't get this terrible floating point stuff because you're not getting this cancellation of terms. Sound familiar, or you haven't seen it yet? Haven't seen it yet? Oh, anyway, that's kind of what's going on with that one for question 3. If after the break, if you've got a particular question about question 3, please come and tell me and I can go through it. We'll go through it in a bit more detail after the break. Cool. That's what we got to. Auto diff's cool, but we don't need to know about it. It's just interesting. Okay, so I won't spend too long on this part. We've already talked about it a little bit. It's just one of these interesting things that numerical integration is really important. Typically, you've got a function you want to evaluate on the integral over a domain. So again, the way the applied method, the pure mathematics method of like, what is an integral? It's like a Riemann sum. So let's use that approximation scheme to derive an algorithm. So we cut it up into little boxes, and basically that's the idea behind these guys. So I don't know if I drew a picture of this. No, that's for later. Drawn a picture before. You guys have seen it 100 times. It's like, in terms of integrals, there's no question on the homework about it, so you don't need to worry about it too much. But basically, first approximation, I'll see how well I can draw really quickly. First approximation would be, I've got a function, and it looks like this. Now, trying to draw on the fly with one of these things is error prone. And the first approximation is you just get little boxes. So sum of little boxes, just this straight Riemann sum idea that you would have seen in maths a lot of times. So you just make boxes and add them up. That's the first thing you might try. Now that's generally a little bit terrible. And the first thing you might think of doing to improve this error estimate is, rather than going, so just to be clear, that's what this expression means. So we're going to go from A to B. We're going to go at some midpoint. So it's called the midpoint rule. This basic one is you just take a point of the function in the middle. So I'm just looking at one of these little boxes. I'm going to actually get it in the right spot though. So at the midpoint, it's evaluating the function point, and you've got some width. So midpoint rule is just a rectangle. So this is the base length, this is the height. You iterate this at multiple points along the function. That's one way you can get an integral. Next order method is to fit a straight line. So instead of this sort of crude thing, what you might think of doing is we're going to go, let's change the color. So we go at the start of the box. Then the second one. So intuition would say that this is going to be a much better approximation for the integral. So this, follow a straight line approximation is going to be much closer to following the curve than than just putting a box there. So that's this guy. So you take, so the notation here. So I'm going to go over this because it's really similar for when you get to Eulers Method and things like that for differentiation and integration like this. So there's a real big similarity between these integration methods and the higher order methods you'd use for differential equations. So it's sort of the same. That's why it might feel like I'm banging on about something that's not so interesting, but it's, in a way, it's kind of similar. So you can see that you take this and this. Then we go to the next higher order method, which I'm not even going to try to draw, which is you fit a polynomial. So rather than having a straight line, you can have an interpolating polynomial, second degree, so quadratic, that goes from this point to this point. You got a bit of freedom of choice about which polynomial you choose. You choose Lagrange interpolating polynomials, and that's the one that you use for these methods. If you do that, because it's second degree, you need another point in the middle. So that's this. You evaluate it at the start, at the middle, at the end. So it's a computational complexity cost, just for doing one little box anyway, that you have to do another function evaluation in the middle. It's all right when you iterate this though. It turns into a different formula. So this is a higher order method. There's a whole thing that go out to infinity. You don't tend to worry about them going much higher because the error converges so quickly. The error terms cancel away so quickly that you don't need to do those higher order ones. You don't really need much beyond Simpson's method usually. Yeah, so it reduces as the polynomial order increases. It gets more complicated though, so you don't really, you sort of cut it off at some point. The whole family of these things are called Newton-Cotes formulas. They go off forever. What I think is interesting to look at is what this looks like is it's like a weighted average of points within the function. So the way to think about these things is like there's not much more when you're doing a summation than just doing a weighted average of points. It's like this one's just, you take this point, divided by 2. It's just straight average. This one's a little bit weirder because you weight the midpoint more and do some funny thing at the front. But they're just like weighted averages. That's interesting, and it's to do with fitting a polynomial, so successively higher orders. Yeah, they reduce really quickly. I've got a little demo here. I don't know if this is, it might be useful to see, like we're passing a function in. So I won't copy paste to the Julia REPL, but we'll just have a rough idea of what's going on is that pass a function in, we've got a start and an end point, and I'm passing a method. So what I'm doing here is I'm just doing a simple application of these rules I just wrote out. So, if it's the first one, you evaluate f at the midpoint. Otherwise, if it's Simpson's, you do this funny weighted average with a 6 out the front. So you weight the midpoint more. I've got two functions here that we're going to have a look at. So they're both a bit funny, so it might be worth, I'll just start up plots so you can get an idea of what they look like. I picked a really funny function here for this f1. It's an exponential of a cos. And the other one's just exponential. So that's like a normal function. So I guess this f2 is more interesting to start with. So I've pre-allocated an array of floats. And what I'm going to do is I'm going to go through a range of points and I'm going to evaluate. So this guy goes from 0 to 2 pi. I know analytically, because I looked it up for this one, it's a Bessel, to do with a Bessel function for this funny 10 cos thing, but the other one's just, integrate exponential, you get an exponential, you evaluate it at 2 pi, you get 2 pi, you evaluate it at 0, you get 1, 2 pi minus 1. That's pretty straightforward. So what you do is we're going to go through that range, we're going to apply the, apply the Riemann sum with both of these two methods, so midpoint and Simpson's method, for both of these two functions. And then some plotting stuff. So plotting two plots on the same plot. I've given this one a handle P1, this one a handle P2. Want to get the plot with both of them together, just plot P1, P2. A little bit funny. So you can, I've just put on, yeah, so it's the error in one method compared to analytic. This is just a straight error. So I've done the log of the error, not relative error in this case. This one's just absolute error. because we're not trying to show floating point stuff. When you're doing the derivative stuff, we're interested in floating point stuff. So done it as relative error. But you get this picture that, the midpoint's terrible and Simpson's method is way better. So much, 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 much better. It's decaying really quickly compared to midpoint error. So this is, this intuition of looking at this picture and going, yeah, that looks stupid. Why would you do that? It's kind of funny though. So the point I'm trying to make, and when you do the homework, there's question 6, right? We've got a method that seems superficially worse, but does really well. This is another one of those cases where, because of the structure of the equation, the dumb method works really well. And it's surprising. So I guess that's the point I'm trying to show on these two plots, is that if you look at Simpsons and midpoint for this funny x cos, so this funny periodic function, the exponential will smooth out all the derivatives. So this is a really smooth function. It's periodic. For smooth periodic functions, midpoint method has really, really good convergence properties. It's super geometric, which is kind of weird. So yeah, that's kind of interesting. So I remember I put this in here because, has anyone heard of fast Fourier transform? Is that something that's come up for you guys yet? So if you do digital signal processing, you'll see fast Fourier transform. So you probably should know what a Fourier transform is, maybe. You do this integral transform into the frequency domain of an equation, and it's got all these useful properties, like usually for solving differential equations. To turn something, a differential equation into an algebraic equation, you've got some analytic techniques to use on it. Fast Fourier transform does not use these higher order terms. It uses this one. That bothered me when I first learned about it, because the fast Fourier transform, if you're thinking of, let's see if I can get, no, Wikipedia is not there. That's really confusing. So we're doing a Fourier transform. Superficially, so this is the equation. So you're doing this sum over frequencies for all these k's. So superficially, this looks like an n-squared algorithm. When you do fast Fourier transform, it's n log n. So this is approximating an integral with this midpoint type rule. Superficially, it looks n-squared. You can do a trick that's a lot like the tricks you guys would have done in the sorting stuff to make it n log n. So you can break it down into little problems, doing a divide and conquer thing for the fast Fourier transform, and you can get this n log n algorithm. And it seems like they've given up. When I first read about this, I thought, they've given up a lot by going to this silly integration method when they could have done a higher order one. But it's actually more clever than that, because you're usually worrying about signals. Signals are usually periodic. So if you're taking a smooth periodic function, they actually have good convergence properties. So it's kind of a magical algorithm. This guy comes up in, so everyone's probably heard of JPEGs. So that should be, they're actually part of the compression algorithm for JPEGs is using a fast Fourier transform. Kind of, it's actually a discrete cosine transform, but that's part of it. So it's like one of these algorithms. I'll talk later on when we do a little bit about linear algebra. I'll do a demo of image compression, and you can see how good JPEG is. It's kind of amazing how much smaller you can make an image with doing this spectral decomposition stuff. Cool. Okay. So it's pretty straightforward to go from these univariate methods to higher order methods. They've got a funny name. So when you go off and you see this stuff, you'll see Quadrature methods, they call it. And they tend to call the univariate ones Quadrature methods. So they're basically the same idea. And I talked about this earlier, that the biggest problem you're going to have is that there's a scaling problem. There's a really severe scaling problem with dimension. As you go to larger and larger dimensions, these methods just fall apart completely. So 3, 4 dimensions, you're good. You have to do something quite different for higher dimensions. And they come up all the time. In my career, I'm doing integration on higher order spaces much, much more frequently than lower order stuff. It comes up all the time in statistics. Yeah, so we can see an example here. There's a function. This is a good library for doing Quadrature methods in higher order spaces. So we've got a Gaussian. So hopefully you can see that. And iterating through dimensions. So starting from a one-dimensional normal distribution to a two-dimensional to a three-dimensional, with a fixed budget for how many evaluations it's allowed to do before it stops. Then we're just printing this out. So what you can see is like, it's got some internal estimate of the error as you go through. It should be 1. It's a normal distribution. It's a probability distribution. It should integrate to 1. It goes down. You start to get up to, it becomes non-negligible at about dimension 7, starts blowing up and starts becoming terrible at dimension 10. So you need to be a bit more clever and you need to be careful. So this is being really clever. So this method is redefining that domain. So one of the tricks you can do with integrals and differential equations is adapting your step size. So if the function's doing something boring, like it's really flat, you can take big steps. So if you can work out that you can get away with a big step, just do that. But if it's changing really quickly, you need to shrink the steps up in that region. So it's doing this adaptive meshing stuff to try and do the best it can on this fixed budget. And by dimension 10, for something simple, it's just a normal distribution. It's not like it's really jagged and all over the place. It's doing a fairly terrible job. If you're interested, I can give you a demonstration of what you might do for higher order dimensions, but I'll skip that for now. If you're interested, I'll go back to it. Any questions on integration? Because that was pretty quick. Happy, sad, good? Good, okay, cool. All right, so this is probably more where you guys are going to want to come into for this stuff. So questions 5 and 6. So I keep forgetting you guys are second year, how much differential equations have you done? You probably are getting it all in different courses all at the same time. It's like, they're sort of like all of, differential equations are like all through physics, all through engineering, all through applied maths. It's like, it's the backbone of all of science, really. It's like differential equations for modeling physical phenomena are what you do. They're 2 types. If you have a normal derivative, simple derivatives of just like with respect to one variable. Ordinary differential equations on the other side, if you've got, derivatives in different directions. So physics models like fluid dynamics or elasticity in solids, you have to worry about partial differential equations. Partial differential equations, you have to be really careful when you're doing numerical methods. So this is way beyond, this will come up later, but the lessons you learn mucking around with ordinary differential equations, you'll learn that it gets worse for partial differential equations. So the things that can go wrong when you're solving ODEs will also go wrong, and some new stuff when you go to partial differential equations. It's kind of interesting. It's good to have a healthy skepticism when someone shows you simulations of physical phenomena, because there's so much that can go wrong numerically that you sort of have to have a lot of trust that they know what they're doing and they're doing the right thing. You guys should see that. So we're focusing on a particular subset of ordinary differential equations you might want to solve numerically, which is initial value problems. So we've got a set of differential equations and we have an initial value. So there's other versions that you want to solve. So there's boundary value problems where you know where it starts and you know where it finishes and you want to see what happened in between. A little bit trickier to deal with. Initial value problems, really useful. It's like, that's how physics works. You throw a ball up in the air, what happens? It's like, the initial position and velocity, you're trying to track where it's going to go. It's not too hard. It's got a really strong similarity back to these integration methods. There's kind of things you want to do, basically the same kind of things. This intuition that you get the algorithm from the definition. So, forward differences. We've got a differential equation. We're going to have a look at what happens one step ahead. We want to know we've got an equation that relates the slope to a function, and we want to know what's happening, as it goes forward. So we can go, again, this stuff about finite differences. So back to this stuff. So we have a derivative with respect to one variable, and we can say that's approximately like going a step forward, look at the difference divided by h. Now, this stuff about numerical derivatives, this sort of conflict of what you're trying to do. It's pretty rare. Like, I don't think I've had much occasion, some occasions to actually do numerical derivatives. It's like you'd use automatic differentiation as the default these days, but it's not as common. It's like trying to do differential equations. That's a thing that comes up. You want to know derivatives when you're trying to look at sensitivities to stuff. So it does come up. But there's a tension here because you never ever, because we're thinking of like, this defines an algorithm for how you might go forward in time. This one directly. So the first one, you know, I think, what do we want to say? What do I want to say? So we've got an example here of a differential equation. This is a second order differential equation. I'll go back to the start. I'll come back to this one, I think. So how much, I guess I'll do a quick poll. Have you done much work with differential equations so far, or is it kind of new? Anyone not done much with differential equations? Like, how much background do I need to give you before we start? Is anyone like, I don't really know much about them at all? Math. Okay. Okay, cool. So you've done it before. I don't need to say too much of that setup of why you'd want to do these things. This thing of an initial value problem, so you only know the starting value. And so a forward difference is that, like, central difference doesn't make much sense, like you're doing in your homework, because you don't know. You want to have this algorithm for going from this point forward. So doing forward differences makes the most sense. And this most obvious one is called Eulers Method. I did right here. So let's go through this one. So if you've got a differential, like the easiest differential equation you might come across is, we'll go dy dt equals minus y. So that's pretty straightforward. That's like the easiest one, the easiest non-trivial one. It's not constant. It's going to come up with a function that's kind of interesting. Solving this guy, does anyone just know off the top of the head what the answer to that is, so we can work with it? Yep. T for this guy. So if you wanted to solve it, you know, you can go take this guy over the other side, do integration by parts, you get a log, the expert. The A comes in from the initial condition. So whatever your initial condition is, this is just this thing that decays down. That's kind of the easiest one. So if we look at forward differences, we're going to say, so we can say our functions like dy dt equals f of y and t. Okay, so in this case, where f y t equals minus y. So that's really simple. So what we're going to do is we do a forward difference approximation, and we know the value of this guy at 0. So let's just say we know y at t equals 0 equals, say, 1. So what we want to do is we want to start from here. Oh, yes? Oh, sorry. Oh, it's hidden behind the chat. Oh, this one's coming up here. Sorry, guys. Sorry. Okay, so we know the initial value, and we want to try and do some approximation of the derivative to get a hint about what happens next. So this would be forward, where forward differences comes in. So we go dy dt is approximately, geez, I've got to press the right buttons. Y at t plus some small step, I'll call it dt here, minus y of t. How many times can I press the wrong button? Divided by dt. So that's just this approximation. You see 100 times forward difference approximation to the derivative. We want to rearrange that so we can get a thing that we go. We start at a point and we can march forward and work out what happens into the future. So rearrange that. I hope you're happy with me not getting it wrong. We care about what happens at the next time step. So that's dt equals, I've got it over here so I won't get it wrong. So yeah, so we're going to go y of t plus dt times f y t. So that's this really simple just rearrangement of this guy. So this guy equals f of y t. We're going to go, we've got our start. So we can, this is a recursive equation. We start at t equals 0, and we know what happens at dt into the future. Let's just do it painfully. So we'll say t, that's a lot of t's, 0, 0.01, 2, 2. Okay. Now, our f of y equals minus y. Happy with that? That's what, but t's not in there, so I'm just ignoring it. So we're going to set up an anonymous function, set up this one-line function that says that f of y equals minus y. So if I go f of 0, 0, if I go for 1, it's minus 1, flips it around. Okay, so if we're going to go one step into the future, so we'll fix the dt, and we get our dt from here. So dt equals 0.01, t equals, is that big enough for you guys to see, or do you want me to make it a little bit bigger? It's okay. Okay, so, and we're going to start at some initial point. We're going to go y0 equals 1. Okay, we're just doing this in the REP. We'll think about how to make it into a function in a second. So if we want to go one step ahead, we just apply this rule. So we're going to go, okay, our initial value is y0. So we're just looking at this side of the equation here, this part. So y0 plus dt times f of y0. Okay. That's our function. So the first step is going to be this thing plus the t minus this thing. So it goes a little bit down. So we started at y0, was 1, goes a little bit down. It goes a little bit down. So if we're going to turn this into a function, I did it already. So let's try and make it a little bit neater for you guys so you can look at it. Okay. So the kind of thing you'd want to do is you take a function as an input, you take an initial value, and you take a time vector. So what you're going to do is pre-populate this guy with zeros to length of t, and you know the first value of this y is going to be y0. Then the kind of thing you want to do is you want to step through this guy. So you could go it depends on how you want to diddle around with the indices, but I'm going to go from 1 to the length of t minus 1. I'm going to say, I've made it so in this one, I could have variable time steps. You could fix the time steps, that's fine. But if you want to make it more flexible, you might want to define a t range that changes. That's just the difference between this time step, the I+1th time step is the one I'm currently at, and the previous. So, but they're fixed for what I've done anyway, so it doesn't really matter. I might have got that, probably want to do it the other way around maybe. Working out which dt is actually the right one. So this is the same thing. I'm just applying this. So I'm going dt, f of y, t. So it should be a function of two things, return y. Okay, so Euler. Okay, so dy dt just equals minus y. That's fine. Okay. Oh, sorry. Yeah, let's not worry about that. Okay. So why? Oh, well, let's just go. I called it F, didn't I? See if that guy works. No, because it takes two inputs. So let's redefine F of, we'll make it more generic. So it needs two inputs. Make sure we got it right with our function. So the first one's the y input, second one's the t input. F of y, t. Same thing, it's just got two inputs, doesn't do anything with the second one. That makes it more flexible. So this is our initial condition of 1, and we're going to put t in here. Cool, so we get some output. Hopefully that looks right. So let's check what we got. Y, Euler. Okay, so we could go plot t, see what happens. Plotting is really slow to start. Hey, so we got that. That looks reasonable. So, you know, we'll check it, you know. Okay, and then we'll probably want to do, so I'm going to plot on the same, so you do plot with an exclamation mark to plot another thing on the same plot. We can do this x of minus t. So broadcasting over t, and that looks pretty good. So that's basically how Euler's method works. So superficially, that looks good. So any observations from anyone about computational complexities? Like, what do you want to do to make this as fast as possible? Yeah, that's exactly it. So you'll do it's linear with the number, the step size. So if you can make the step size as big as possible, it will go as fast as possible. So let's do that. So we had dt. Let's try and make it big. And will that be big enough to make it explode? That's the question. Okay. Plot y Euler again. All right, it's not looking too bad. Let's make t bigger. dt even bigger. Let's try 1. Oh, I didn't change t. Maybe I'll go back quickly. I didn't change t. This is why you write scripts and not hack around in. We'll go back to point 1. I forgot to redefine this guy, I'm pretty sure. Maybe that was fine though. Yeah, no, that was terrible. I didn't change t. That's what happened with the last one. It looked the same as before. So this suddenly got worse. So we increased our step size by an order of magnitude, but the results got bad. For short times, it's still fine. It's actually still fine. That's, you know, if you're only worried about a tiny horizon, like, you know, tiny bit in the future, it's much quicker. Just do that. So we'll make the t ludicrous. We'll go up to 1. Remember to make t this time. Y Euler. Oh, it just jumps down to 0. So that's bad now. But, you know, we made it way too big. So that's actually the problem. So with differential equations, more so than the integration methods, because you're starting from the starting point and going forwards, these errors accumulate at every time step. So it's actually bad. You want this tension of having the numerical derivative as accurate as possible with a big time step is what you really, really, really want to be able to do. It might be a really obvious point, but I guess it wasn't obvious to me when I was going through undergrad, is like most differential equations you can't solve analytically. Like you have no chance. Anything nonlinear, you have to do numerical methods basically. Very clever people will spend a long time figuring it out. This is the only thing you've got. So this is actually a really important problem to be able to do this. So what you really want to be able to do is have huge time steps, go as fast as possible so you're not waiting forever. You could do Euler with tiny, tiny, tiny steps if you don't worry about the compute time, but you know, for certain problems, that's going to be a huge problem. So I had a picture. I'm sure I had a picture. Euler's method works for systems of ODEs, systems of first order ODEs. So usually you'll have like a second order equation or a system of second order equations, and you want to turn them into a system of first order differential equations. We made this easy for you in the assignment. We gave you the system of first order equations. So it's more like just plugging in Euler's method and plugging in the higher order methods. So first step you always do is you write this as a system of first order ODEs. And I remember getting really confused by this. And it's just like, it's really obvious. You just go, oh, the first derivative, I'm going to call it V. And then the derivative of v is just this function if you've got a second order one. That's all you do, and you've got a system. It's easy. So as an operation on a vector, it's the same thing. You're just going to go x, this big X. Oh, sorry. I called it big X and didn't change it everywhere, but forgive me, please. So it's just the same. You've just got this differential equation with respect to some function on this. Instead of being a univariate thing, it's like it's a vector now. Do exactly the same thing. You can do this forward diff approximation to a vector, plug it in. Euler's method looks exactly the same. It's like the only difference is when you're writing Euler's method, you're going to have to just make sure it works on vectors and returns a vector. It's really straightforward. Hope that's clear and it seems straightforward. This thing I wrote might work. I won't say that it will. It's just like making sure that this guy is a vector, it's the right shape, you've got the right shape for your inputs. So rather than so if you've got a second order equation, you need two initial values. You need an initial condition for the x, sorry, what do we call it? Y. So you need an initial condition for y and you need an initial condition for v to get anywhere. So you need two initial conditions. When you're doing the orbity one, that's the same thing. You should have two positions, two velocities, because it's a fourth order, it's a system of 4 ODEs. Kind of trivial in that way. Okay. This next one though, it's the same pattern. It's like everything's a weighted average. This fourth order RungeKutta method is a similar idea. It's like, instead of just doing one point, we're going to evaluate at a bunch of points and take a weighted average of these different approximations. So you can go through the maths in other courses, I'm sure, on numerical methods. They'll be super rigorous and go like, oh, you choose this as being 6, and you choose this as 2, and this is 2, and this is 6, because it cancels some errors. Basically, it's just a weighted average of terms. It's like, this guy's like Euler's method. This guy's with some halfway step, another halfway step, and another one. If you look though, there's like this resemblance of this fourth order RK. That's why I talked about it. And this guy, they're actually kind of similar. You've got the 6th term, and there's this 2 at half points. Superficially, they look really similar. And if you think about fundamental theorem of calculus, they actually are quite similar. So I just wanted to point that out. We've got an extension. I'll go to the homework. Where is he? So there's a lot of stuff here that you don't need to know. It's there for completeness. So this thing's called a symplectic integrator. There's equations of motion. If there's anyone do physics and Hamiltonian systems come up yet, or is that like terrifying new word for all of you? Some people are nodding, some people. It's just a word. It's like the thing to take away is that there's this conserved quantity. So this conserved quantity called energy. Like energy is not changing with time. This is a fixed energy system. Planets going around a star, or they're all going around their center of mass. It's a fixed energy system. You have a special equations of motion you can derive for these things. They're called a Hamiltonian system. I don't care if you know that or not. I put it here if you're interested. It probably just terrified you. Don't need to know that. Really, what you worry about is they have this thing, this special thing about them called symplectic geometry. Oh, yeah? Okay.
I tried to derive the solution to that because I didn't realize the F was the F in the last question.
Oh, it's not quite the F, right? It's really the second order system you use for these ones. So it's this one. You have a system. That's the FU. Oh, okay, yeah. Oh, okay. All right. Sorry. Sorry. Okay, I'll take that. Yeah, okay. Yeah. Okay, so 5 and 6 had that problem. Yeah. Yeah. It's pre-work terrifying pre-work for an easy thing. Sorry, everyone, if that's really confusing. It's more just for completeness, because it's like everyone's coming in from a different spot. You might want to know why. Yeah, we'll make it more obvious next time. Maybe change it now. If anyone else isn't in this lecture and they want to know. It's like a bit of terrifying pre-work. Really, this interesting thing is that energy is conserved for the system, and you can write it as a system of second order. You don't need these first order terms at all, really. You can just write it as a system of second order equations. So when you go through in this derivation up the top, there's this form. You notice, like, as I was saying with this Eulers method, you just write V for the first order one and then go blah. That's kind of what's going on with here. Like, these are sort of trivial differential equations, these bottom two. Whereas this one you can go with, but you make it into this form to work with Eulers method and to work with RK4. Then you can just sort of plug them into these methods. But really, the equations of motion just have this special second order form. Terrifying pre-work, just down to this guy. So what you're working with is this second order system, is this FU here. That's a really unfortunate acronym for all that, what you just said. Yeah, so you're just working with this system of equations. And the idea with a symplectic integrator, this one's a really easy one called the leapfrog method, is because it's a physical system, they're going to call it velocity. There's an intermediate velocity you use that you update first. So you do this thing that's like Eulers method, it's this spot in the middle, and then you use that V half to update the next position and the next velocity. And these look a lot like Eulers method type updates, but you use this step again in the second one. That's why it's called leapfrog. It's like you do this intermediate velocity, then you do position, then you use that position to do the next velocity. That's why it's called leapfrog. Now, there's a point here that why we're getting you guys to look at this is that what looks easier, like this method is kind of straightforward. Like, it's not much more than Eulers method with a couple of more steps. Compare that to, or in the notes, we got the RK4 one. So I should have opened a new window. Yeah, so RK4, this one's way more complicated. It's got way more steps. Leapfrog seems dumb, but I don't know where people have gotten to with your homework. This is the sort of thing we want you to look for. Leapfrog method, even though it's a dumb method, it actually works way better than either of these two other methods because it has a conserved quantity that's almost like the energy of the real system. So one of the things you can show with symplectic integrators is they almost conserve energy in the same way that the original system did. And they're time reversible as well. So Eulers method, if you try and go backwards in time, you end up in a different spot. Leave this is for someone who's super keen, they can look through. If you look through the leapfrog method, if you go forward to the next spot, you can actually go back to the spot you were at. So this is really important for like periodic systems where they're coming back around. They'll be you want them to be reversible. Hamiltonian systems are reversible in time, something from physics. But so the point, educational point I'm trying to get to with this one is that if you have a special, this one, my point for you guys is when you go out, is if you know something special about your problem, sometimes something dumber will work a lot better than you expect it to. You can't just rely, there's no one best method. Exploiting the structure of your problem will give you the best results in general. Any questions on that? I can go through it a little bit more later if you want more details of like how you might do RK4 just as another example. Or anyone happy? Happy? I'll show you something just because I did it on the, made you guys suffer, so I thought I'd suffer myself. I did the 4-body problem. So one of these things that you increase the complexity, everything gets harder. This problem for you guys is it's a nice simple one. They're just conic sections. So for yours, it's an ellipse. We'll just do ellipses around the sun. So, it's easy to work out analytically you can actually work out analytically what the solution should be if you want to verify it. I haven't made you guys do that because it's a bit cruel. As soon as you get to more than 2-body problems, it's not conic sections anymore. It's actually a chaotic system, and small changes in conditions and numerical errors will explode. So I did the four-body version of this. So I went through and did the derivation for what the four-body problem would be. I can show you guys what that looks like. So this is four things orbiting around a center of mass. And I've done the leapfrog integrated to this guy. Now, this is why you do numerical methods. Could you imagine what the equation for that looks like? And I even needed to do dirty tricks to make this actually work. I had to change the equations of motion to make it more stable. So there's lots of features of differential equations you can see in this when you go to the start that are interesting. It's actually an unstable system. What I've started off with four things starting in a cross, and they've got a velocity like this going around in a clockwise around a circle. Should be able to see that at the start. And what you see is there's this growing perturbation. Right? They go in and out, they're getting a little bit faster, getting a little bit faster. And they get to a certain critical speed and they just throw each other apart. This is why numerical methods are important. Like, how can you understand the behavior of these systems without numerical methods? Things like floating point error and numerical derivatives will make huge difference in the solution you get. So even though this is a trajectory we generated from an initial condition, do you trust it at all? If I change it by epsilon, I'll probably get something different. Change it by epsilon again, I'll get something else. You know, these complicated nonlinear systems will give you complicated, crazy answers, and you could never guess from the structure. Like the equations written down don't look too much different from what you guys have got in your assignment. Yeah, it's kind of mad. That's why you do numerical methods. There is no equation you can write down analytically for this kind of stuff. And you have to be careful with the numerical methods. Did I get the step size right? Does this do something completely different? Because I don't have access to an actual analytic solution. If I change the step size, maybe I get something different. Maybe I have to reduce the step sizes down and see if it converges towards something before I trust it. There's millions of critical safety things, like driving a car, like the cruise control for a car. That's a nonlinear system. It can have very complicated dynamics. Like if the wheels are slipping, it's really complicated. Real systems are complicated, and how you would predict these things forward to do any sort of control estimation is really, really difficult. Okay, cool. I'm going to take a 10-minute break. If you have particular questions about the homework you want me to do, please come up and ask me, and I'll try and summarize in my head what we can go through.
It says how many floating point operations. Yeah. So like for something. Yeah.
So just look at that.
No, it's like what counts as a so like a square root. There's an algorithm somewhere that's doing a bunch of operations. Can we just say that's one?
Just say that's one. That's good enough.
Okay, good. Okay, cool.
Order of floating point operations. Just count how many.
Just how many? Yeah.
How many functions?
Yeah. I was freaking out. I was like,
no, sorry. Did you? Yeah. So you would have done a square root for doing the radius, right?
Yeah, right. And then there's a cube root.
Yeah. Sorry, I'm being imprecise with what I wrote. Yeah, very sorry.
Okay.
Yeah. Hello. Yeah, that's fine.
I'm just going to explain what's happening. So that was the example from the course, from the lecture notes from the lectures. When you were like printing the, the way that.
Oh, this one you asked. So this was you. Okay, sorry, I don't know the answer to faces. Okay, so you used SciGo to give you the derivative.
Yeah, and I've gotten it to work now with the indexing it,
yep.
like you said. But it's coming back, so that's why I'm plotting it, kind of, except I just got like all of the like Airford 1 complex, like all of the types for function 1, and then I've got all of them for function 2, and then all of them for, like, also there's 9 of them.
Yep.
And then I've chucked them into like
an
array.
Yep.
And I'm trying to print them, but I'm getting like an overload.
It's probably how you're constructing the vector. I'll show you online. That's okay. I don't know if I should be wearing a mask on. Anyway,
I think as the teacher, you're exempt. So.
okay. So you've got error 1. Let's just say this is 1s. Error 2, just say.
Yeah.
And you're going the concatenation, the two things you're doing together, error 1, 2,
yeah.
is a matrix.
Yeah.
It might not be what you want. You might want an array of arrays.
Okay. How come that works in the lectures to like plot? Would it be easier to just do the plot and exclamation mark thing, like
That's
plot
what
all
I
of them
always do.
individually and just
That's what I
yeah,
do.
I might just do that then. Like,
That's, you see, I do that
Yeah.
in my notes all the time.
I think I ended up.
It'll be
getting-
something about the shapes are wrong.
Right. Okay. Yeah.
You know, like they're inconsistent dimensions.
Yeah. Yeah.
You'll see that when you plot them one at a time as well. But if the range is the same, you plot it one at a time. At least you know which one's broken. At least.
Yep. Yeah. Okay. Yeah. I'll try that.
Okay.
Thanks.
I reckon it'll look like with fuzz.
Yeah.
And then the
We've
other
got
one
two
will be
look pretty
something
much
like,
the same, like a little bit different.
and then the other one will go something like.
I've got two that look something like this.
Yep.
One
Oh
that's
yeah.
not quite as dramatic.
And you know,
And then the other one's just a straight line.
it's just a straight line for all values.
Well,
Um,
it's just so low. So I can get it on the log. As soon as I try and put it on the log.
Does it come back up like this? This is what I would expect, that it, at some point, probably for
If
translated
I-
across
If I
actually.
put the H slow enough to make it not just be a straight line at the bottom,
Yep.
then the others just stop working
See,
if they're on the same plot.
you should, this guy should at some point start to act like you have an error like the others. I'd expect it to come up. It's kind of weird if it doesn't.
It's because it's not on the log plot probably. Because if I put it on the log plot, I was getting issues with it being 0.
Oh, okay, that one. Okay, I know that one. Then. So
So I just changed it.
because it's a log plot, you're going to have errors of precisely 0.
Yeah.
Yeah. So, you know, these low ones will be something like 0, 0, Fs, and then normal stuff.
Yeah.
Blah, blah, blah. If you take the log of that, those first guys are going to screw you over.
Yeah. Yeah.
So what I would do is I would, function to use is clamp. Clamp limits to a range. You can broadcast this like, so you take your value and you're going to, this is the lowest value and this is the highest value. So with these errors, you could go clamp broadcast. And I don't care if you're below X because I don't even know what that means, right?
Yeah.
For the low side, and on the high side, you can go inf, whatever.
Yeah.
So that'll be floating point error.
Okay.
And then if you go plot errors, I can't remember can you remember the magic spell? It would be something log
Oh,
axis. Is it?
Axis, sorry, x-axis. Log x and y axis.
Oh, so that should plot like that.
Yeah,
I was
okay,
saying.
cool.
And you know, maybe put a special plot in here going, this is floating point error. If it's below this, can't actually tell. Whereas if you just did the other one,
Yeah, it just
oh,
dies.
sorry. It's like there. I did this guy, I don't know what's going on.
Yeah.
Yeah, and they get nothing, and there's minus inf down there. It's crazy.
Well, that fixes the Quadrature.
Yeah. So this is this thing of like when you go to these guys.
Yeah, because it was just basically 0 for a while. And that's where I was getting issues. It's that
Yeah.
problem.
If your rel tol's in here, you can't actually tell what the answer is. So there's no point saying below that for floating point.
Sweet. Awesome.
Yeah.
Yeah, another way to do it, but this question where you have got, this is a worked for this method where I created P, right, that had structure P, and I like got L, put it in a vector, and then tossed it through structure P to create all the different structure P's.
Yep.
With map, and then one was function, and then mapping it to like each of the elements, like that way, and it worked for this method. And it printed the right thing, but I couldn't get it to work for this one.
Do you understand what it's doing if you want to?
So it's like element 1, like column 1, column 2.
Yep.
And then just taking all the rows of it, right? Because the
Take that slice.
yeah, that's
So you need to.
Sorry, but the wrong
I can
one.
actually. I'll go through this one.
Yeah. Right.
You need to go all by one. It doesn't really
Yeah.
matter which one.
Because I did that, but it was giving me like a wacky error, and I couldn't seem to get rid of it. It worked when I wasn't going through all of the different structural keys, and then just like pulled it at the end, like pull all the L's at the
I
end.
mean,
went to the,
what I'm saying. This 1 to 2, 3.
Yeah.
Are you adapting that for
Yeah.
L?
Yeah,
you
so I did 1 colon and then L minus 1.
Yep.
And then all of the rows. Go with that, and then 1 was L as well, and then B, I think I did zeros, and then well, hang on, try B. I can't remember exactly what you noted, but like that's just the last column, just the last column.
The last
of-
one should be 1.
and should be 1.
Yep.
And I did that, but it gave me, I can't remember the error. But it just, for some reason, didn't work, because as far as I can understand, that was like the way to make it the cleanest was to like make it the cleanest first, and then just go through all of the methods
Yeah.
afterwards, and then just. But it,
So your second one is 9.
yeah, I mean, I think
Our
this is
method
1
should
and
always
this is 2. This one was great and worked fine, but this one just, I don't, yeah, it
I
was,
can actually try that one.
yeah, right, okay.
Try it.
Could I show you it later?
Yeah.
Yeah, I can't work out. Just doing everything right.
And you understand.
Yeah, if you're on this one, but they work with the way that you don't make it.
Okay.
With the other way, I don't understand that they work, so
Okay.
I understand the other two of them.
Okay.
I don't think it's just going to the second one.
All right. Okay. So, but you understand where this comes from, like why this process. Does that make any sense?
A little bit. You only did explain it today, and it made sense at the time,
Okay.
and it's gone out of my brain now.
Yeah.
Oh, my brain,
It's
like,
really
let's
just-
not think about that.
It's really just that you don't need it all.
Right.
Can't invoke this directly. This is like, this is a constraint. Probability.
Yeah.
So you just check out one of the levels as a constraint. So it should work.
It worked when I can't remember exactly the other method for any point where about but it worked with the one where you can like create a P at the beginning and just like kind of,
Yeah.
it worked that way, but it didn't work with creating it and then going through it. Yeah. I'll
All right, back into it. How about you vote in the chat? Like, where do we start? Does anyone want particularly? Someone said about help with question 2. Is that everyone yay for that one? Okay, cool. One person who agrees gets what they want with a lesson in life. Someone said no. Okay. Okay. Let's have a look. Okay. Okay, so we've covered, okay. I'll make a plan. I'm sort of a bit scatterbrained today. So let's make a plan what we can do. Going through Eulers Method, was that clear? How you might implement that? Making sense? I might walk you through RK4, just like for help. Like that might make a bit of sense. See if I can get it wrong. If you understand RK4, I think Leapfrog's really straightforward. It's just the same sort of thing. You just apply the recipe. Really, yeah, so we had some questions. Okay. Oh, there's also this differential equations library. I didn't talk about that. I'll come back to that when I talk about this too. So one of the things about Julia is that it has state-of-the-art differential equations library, like best of breed. It's really amazing. It does all these different things. It does stochastic differential equations, so differential equations forced by noise, super important thing. Really difficult too, and it's really, one of the really interesting things is the guy who developed the package invented methods as he was developing it that are brand new, that are state-of-the-art. And Yoni has done some research with him. It's because it's a tiny world. So as this guy was implementing it, he's a really smart dude, just came up with some new stuff that it's like applying these higher order methods to stochastic differential equations is really hard. And he came up with a way to do it. Like, wow, that's cool. You can still do new things in the world. Yeah, so part of the question we asked you is to drive differential equations library. Part of question 6 is like, you know, you had to go yourself. You set up one of these functions that guys are in set of first order equations, set of second order equations, plug them into the library. Have a go at driving the differential equations library and see if how much better. The big thing they'll do that you guys wouldn't do, I'm assuming, as I did a fixed time step method. So same as when I was talking about these high order integration methods, you want to be able to adapt. Like if it's a boring part of space, like this differential equation is not changing, it's basically a constant, you can take huge steps. There's tricks to doing that. We're not teaching them in this course, just for your rough thing. RK45 is like one of the ones that everyone uses. And then what that is you use the 4th order RungeKutta and use the 5th order RungeKutta, and you use the 5th one to work out if the 4th one's a bad estimate, because that should have a better error tolerance. If they're very different, you want to shrink the step size. If they're good, maybe you can increase the step size. So this way you can do bigger steps automatically. So you can automatically adapt what your delta t is at every step. This can go horribly, horribly wrong for a particular type of problem. These are called stiff differential equations. That's when it looks boring and then all of a sudden it changes really quickly. So you have at least two time constants in the system that are really different. If you can imagine like buckling something, it's like if you press on a beam, it falls apart. It's those sorts of problems where there's this nonlinearity that makes it change really quickly, like a breaking wave. Yeah, some state changes really quickly, makes things fall apart really quickly. If you have that sort of system, this adaptive method will die, and you sort of need to know. So education point for you guys going forward, you need to know something about your problem. It's not like you can just plug and play with this stuff. It will go wrong in particular ways for your particular problem. It's not like anyone's worked out a golden method. Everyone should do this. Got an example here. I'll go back to that when I get back to it. Okay, so I might save this guy for the end or for tomorrow. You have to do a bit of linear algebra for question 4. It's pretty straightforward linear algebra. It's basically matrix solve and eigenvalue decomposition. we'll talk a bit more about that stuff. I'm just scanning through to make sure we've got what we need for today. And I want to talk a bit about sparsity, just as another useful thing for you guys to know. So that'll be tomorrow. So tomorrow, I think we'll go through linear algebra, sparsity, and I'll show you this demo of how you do higher order integration, if you're interested. Other than that, we'll go through homework stuff now. So, okay, homework 2. Okay, so question 1's Unix. You should be fine. Has everyone settled on a way of getting the practical B? So this interesting thing is like everything's the same bunch of data formats. If you look at the raw, this is JSON. So JSON's all over the web, you know, and it's a nested data structure. So you can think of it as JavaScript object notation. It's either an object dictionary or an array or a bunch of low-level types. So they're actually kind of nasty to traverse. If you just get a random bit of JSON, you have no context about what it means. You sort of have to do this type checking at every level to work out where you can go next. It's like you get a bit of JSON, it's just a number. Cool, there's nothing else to do. Or it's just a string, nothing to do. Yeah, but you know, it might be a dictionary, it might be an array. It's not clear unless you look. You sort of have to go and look to work out what the structure is going to be. So if you look at the raw JSON, it's like this guy is a signifier for an array is coming. When in the Julia library for parsing JSON, it will go, oh yeah, that sells, blah, blah, blah. That's an array. I'm going to take all these things in. When you've got these key value pairs everywhere else, so it never hurts to just look at that. This is meant to be human readable. It's formatted nicely. You can just go and look at it to start with if you've got an idea about what's going on inside the structure. So it's an array is the first thing to start with. So cells is an array. And each one of these will come in as a dictionary. And the dictionary will have keys. Like the first type will be cell type. Second one will be metadata. Another one will be source. Blah, 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 blah. So source is an array. I think my eyes are really bad. And blah, blah, blah. And then there's markdown cells. They'll be different. So immediately you've got these two types and maybe there's a schema to these two types. So, you know, you might want to do something different. If you're looking for the same key in a markdown cell or what are the other ones? A code cell, they might not exist. So keys that are in the code cells probably won't exist in the markdown cell. So if you're going through these things, you probably want to check which type it is first before you do anything with it. Let's do it. I think I have a local copy of this. So using JSON. Okay, let's see if I have this. I should do. So ls cd source programming course in Julia. What do we got in here? We got markdown. That's the, so where are we getting this guy from? This was practicals. So we've got to navigate to wherever that guy is. I'll do it this way. Programming course with Julia. Practicals Jupyter. Okay. So let's get this out. So path to this guy equals /home source. Everyone else, I'm guessing, is going to be using HTTP requests to just download it off the internet because they don't have a local copy. Is that pretty much what everyone's fallen on? That's fine. I've got it locally. I'll do it a different way. You can do these things. Yep. Cool. I'm just checking, saw that question. So that was in practicals. And which one was it, guys? Practical B. Is that the right one? Cool. So we're going to go. Let's see if I can read it from a file. I've only got this in my. All right. Sorry, I'm just brains a million places. Okay. Maybe we'll do the HTTP. Request get. Okay. Do it the same way you guys are all doing it. That's not Strand. You probably want a better name than Strand Web. I'm just copying old commands that are in my bash history. Okay. Why is that failing? Anyway. Let's go back. I'm too lazy to remember commands. Better name. Okay. Take a little bit of time. Okay, so what's come in is a dictionary to start with. It's an object. So I've got a question. I'll just make sure I answer it. For question 2, when we're creating a CS file, first column is cell number. So this JSON file has a markdown cell and second cell. So it's fourth cell, so first column. I'm not quite sure. I might need a simplification for that question before I can answer. If it doesn't have a theme, is that the question? I'm creating a file, first column is about cell number. Suppose the JSON file only has a markdown cell, and the second cell is what's the fourth cell. I'm not sure I quite understand the question. You might need to have a go at rephrasing that one before I answer it. Okay, so we have a bunch of data in here. If you want to know, like, useful function for dictionary is keys. So prac b data. That's just those things at the front of the dictionary. If you want to get the keys, you can iterate through the keys. You know, if you're generally going through a dictionary, the kind of thing you'll do is for kv in prac data b, you can go at show k, at show type of v. So iterate through the key value pairs, have a look at what's in there. So cells is a vector of type any. NV format mine is an int64. Metadata is a dictionary. And NV format's an int64. Cool. So that first thing of like, what do I do with cells is like, oh, it's like a vector. So it's an array. So rather than going and looking at the JSON and going, oh yeah, it's got this funny square bracket, I can go, oh, it's an array. So we may as well cut that out. So we can go, it's all the questions about cells, right? So we can go cells equals prac b data. Cells, some array, some funny array. Can't look at that, it's too much stuff. So let's just go, because we know it's an array and you're trying to do a bit of interrogative stuff, just look at the first element. So you can either go 1, oh, it's another dictionary, cool. Or another thing you might want to do is go first. Does the same thing, just a little bit clearer. So we get the first one and we're going, oh, it's a cell type. Okay, cool. Let's iterate through cells and see what all the different cell types are. Got to show it. There's no point for Julia. Okay, so we got that. So like looking at that, there's not that many. Markdown, markdown code, markdown, markdown code, markdown, markdown code. All right, cool. So there's only two types. You might want to do a comprehension and go do a similar thing. So maybe I'm going to go C cell type for C in cells. I'll make an array of all those guys. If I want to know what's actually in there, if it was too big, I might go unique. That will just give me the unique elements in that cell. There's only markdown and code. So I'm pretty safe if I've done this unique thing to know, oh, there's only code and markdown. I'm going to do two different things. So, you know, because I'm in the REPL, I can make a loop and counters. You might go count markdown equals 0, count code equals 0. Then you might go for C in cells. I've got to say global because I haven't written a function. If you're doing this yourself, please write a function. So we want to go if C cell type. You probably want to write this a bit neater. Don't hard code it all, but that's fine. If C global count code plus equals 1, else global count. Okay, so hopefully that worked. So finding through, yeah, fiddle through. It's kind of hard because it's this tree-like data structure. It's, you know, you sort of, without knowing the schema, you sort of got to have a poke around and find out what's in there. Was there, just in the chat, was there a particular part of question 2 that people were finding difficult? So I can focus on it rather than just hacking around and doing it all. If anyone wants a particular help with a particular part. Yep. Yep. Yeah, it's like free form. You can be as creative as you want. Just find some interesting things. Yep. Yeah. Was there any other part of this question anyone was stuck on? Was it the string parsing? Was that okay? So if you've suffered and got through it, was that okay? How to find the strings and stuff? Occurs in or contains would be the way I would do it. So you could also split on it. Like that's a bit more yuck, maybe. We didn't teach you guys about regexes, so regular expressions. That's like a better way to do it, but it's beyond what we'd expect for this course. Where can you learn about it? Just find it on the internet. I don't know off the top of my. I'll have a look after the lecture and see if I find a good one. But yeah, I can't say off the top of my head. I'm not the best with them. Some people are really good, but use regexes to find strings. You can use occurs in. You can use split on this character. That would work as well. You have problems with double counting, but if you know how often something's happened, you can just go, oh well, I counted this one. This one's got 4. And when I've counted the ones, I know I counted 4, so I can subtract off 4 from the low-level one. So you're getting unique elements, that sort of tricks. Fine, everyone happy then? Any more questions on 2? Yeah, cool. All right. Numerical derivatives. Help for this one. I think your question, I probably should just tell everyone. Sorry for repeating that. A little bit about floating point. So who had the ticks random thing going? Oh, yeah, ticks. It's complaining about ticks when I do the imaginary one. Did everyone get that? Someone did, yeah. So what's going on? I'll give you an example. And I've got the example here because I was just showing this guy. So typically, so what we were saying, so this is my dodgy plot. Without having done the assignment myself, I expect it to look like this. Maybe this guy's translated, I don't really know. where you'd have method 1, let's change the colors, this is terrible. You'd have method 1, method 2, method 3. So this catastrophic cancellation behavior, and this guy would be really furry over here. Same plots we had in the lecture notes. So doing forward differences, central differences, you might win a little bit with central differences, depends on the function. Can't say. It actually depends very heavily on the function, like what sort of behavior you're going to get, and you should see that. And then because of this, you know, this magic of, I don't know where my stuff's gone. This magic of you don't have to have this cancellation term if you just look at the imaginary part, and you know these errors are going to go away like h squared. You shouldn't see that. What should happen is that this guy goes down, and plotting on a log scale here, and then these guys are very small and sometimes 0, and you know it should be great. It should be like doing automatic differentiation. You should get an error that's down around floating point error. So thing to keep in your mind, we'll go back to the lecture notes. This is a useful plot. Thing to keep in your mind is that if you're looking at relative tolerances, so there were some questions on Piazza about like, how should I report errors? It's an exercise in floating point errors, do relative errors. Anything below the machine epsilon, I don't actually know what the answer is. Like, I can't tell without doing some clever analysis that like what the actual floating point, what the true floating point error stuff's going to be. Unless I've done the derivative, you know, like the stuff about evaluating the function. So for this, I had a question, sorry. I'll go before give me time to think about what my point was. So the third function, does it behave differently from the first two? I'm referring to the function. Yeah, it should change. It should change even within the same function. It should change where you start, where you're actually doing the approximation around. Like a bit where the derivatives are moving really fast, or the value is really big, or the value is really small. It'll change where this optimal thing is. Should change. I'd have to reproduce it to show and see, but it should move around. So yeah, if you're at floating point errors, there's no point reporting errors below floating point errors. It's like precision when you're doing an experiment. If you're going to say it's below 10 to the minus 16, and I don't know what's actually going on below there, it's sort of magical. Don't report errors below 10 to the minus 16. What I would do, so we have this example, hopefully that comes up on the screen. You can see I've got like, oh, these two errors are 0, then the next one's floating point x, and then there's 2e to the minus 5. So they're like 4 points along this graph. Kind of thing you might see, probably bounce around. You might get something like 1e to the minus 24 or something strange. If I go to plot this with y-axis equals log, it's going to take the logarithm of these. So if you're taking the logarithm of a really small number, it's going to get, especially 0, it's going to do some crazy stuff like that. So that's the back end complaining strict ticks not found, is because it's having floating point problems itself when it's taking the log, doesn't know what to do. So, you know, if you just take the log of those errors, you know, you've got a minus infinity in there. That's not great to plot on the same scale. Again, you don't really want to report below floating point anyway. So I would advise clamping. So there's this function clamp. Clamp takes a value. You give it a low value and a high value. If it goes below low, it saturates at low. If it goes above high, it saturates at high. If I say, so yeah, so if I go clamp 1, 2, 3, it'll go to 2. If I go 4, it'll go to 3. Just keeps it in the range, yep, and pushes it to the boundary. So for this one, what you'd probably want to do is something like maybe not 2 and 3 errors. Because it's an array, if you've got this error array, I'd broadcast with the dot, and I'd say on the low side, there's no point going below F's, but on the high side, go to infinity because you're never going to get errors that big. So just to show. So if I do that, if I do the log of this, broadcasting, you know, they're all same numbers now. So if I do this plot log, so clamp Got to type it again. Errors, eps, inf. No complaining, and it draws this line. But if I were doing this, I would put a special dashed line at floating point epsilon as another line on the plot to go, this is floating point error, I've rounded these. You know, I don't know what's going on below there, but it's good because it's definitely below that, but I don't know exactly what the value is. That'll fix up plotting errors. Question 3, cool. Any questions before I go on? No. Okay. Homework 2, help. That's that guy. Okay, this one has that, your wall of text to you know, this is just pre-work so you understand what's going on. Some people are having problems with this one, some people not. Roughly, okay, nasty. Yeah, okay. You're basically given a function. So just go to the questions, right? So you've got these 4 methods. So this stuff's all about Markov chains. So you may or may not have done Markov chains. So it's a bit of lead up to it. There's a special subclass of Markov chain. So Markov chain, really useful. Google's original algorithm was based on analyzing Markov chains for websites. So the idea is that, and actually used, which one? Method 2. They use power method to start with, I think, but maybe a special version of that, Krylov subspace stuff. So anyway, blah, 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 blah. Basically, the model, if you're interested, is you've got some bunch of states. I can draw this one. This one's easy. Got state 1, state 2, state 3. We've got some probability of hopping. I'll do it with curly arrows. Got some probability of hopping from state 1 to state 2. Got some probability of hopping from state 2 to state 3, and same way over here. And you've got all these reverse links too. You know, it could be anywhere. So you've got this bunch of transitions, each with a fixed probability of hopping around. So you'd call like this one, this is like 1, this guy's like 2, this guy's like 3. So you'd say this is the probability of going from 1 to 2, vice versa. This is the probability of going to 2 to 1, this is 2 to 3, 3 to 2, blah, blah, blah. You can write all these transitions into a matrix. You can imagine you're going to get funny stuff, like that's the basic setup for this 3-state one. We could imagine some funny thing where we go, oh yeah. And this is 3 and 4. And I'll get rid of those probabilities because they got the wrong label. But you know, these guys don't talk to each other at all, and they don't even hop to each other. So funny stuff can happen. So only sometimes will you get a stationary distribution. So all this pre-works like giving you the idea that funny stuff can happen. We're going to give you a problem that doesn't have this funny stuff happen. Method 3. Okay, I'll go through all the methods. Okay, that's cool. So basically, the idea is, the first idea to start with, see if it'll come back to where I was. You want to know, if I started at this point, I've got some probability of hopping to 2, I've got some probability of hopping to 3. I could hop around. Hop, hop back, hop over here. Different probabilities. If this one's really high and this one's really high, you're probably just going to go 1, 2, 2, 1, 1, 2, 2, 1, 1, 2, 2, 1, sometimes to 3, blah, 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 depending on all the probabilities. So that's like the intuition version of this thing. And that's going to be method. Sequence of random variables simulate from the Markov chain. So you're going to go just hop around and count how long you were in different states. That's like the easiest, but probably the slowest for small problems. It's actually bad. When you get to really big problems, that's probably all you can do. Like if you're doing hopping around from website to website, that's probably what you'd end up actually. That's probably how you'd simulate it these days, because this graph of transitions is probably too big to have in memory at all. Anyway, so method 4 is simple. You can write this as a matrix equation, and I'll probably get it wrong, but you can write out a matrix that's like P equals some matrix, P1, 2, P2, 2, sorry. 1, 1, if you're allowed to hop back to your own state, 1, 2, P1, 3, depending on how we index these guys, P2, 1, it's hard to write, it would have been easier to do in Julia, P2, 2, P2, 3, etc. P3, 1, I've got it, I'm committed now, P3, 2, P3, 3. Okay. So I've got some matrix of probabilities, all these transition probabilities we could write in. And we're trying to work out what the stationary probability is. So like, if I look a long time into the future, what's the probability of me being at 1? What's the probability of me being at 2? What's the probability of me being at 3? So the thing you could imagine is like taking a starting guess. I could have write it in Julia notation, but anyway, taking a starting guess, and you do, if you weren't simulating stochastically, you could just go, what's the probability of me being in the next state? That's one matrix multiplication of this guy from some starting guess. And then if I do another one, that's like step 2. I propagate those probabilities again. I just multiply, do the matrix multiply again. That's p to the power 2. That's like 2 steps. Like that's what the distribution would be after 2 steps. So if I do that 3, 4, 5, 6, that's should, if you set up if the type of matrix is right, that's what you'll be in the final state when that's really big. So one thing you can do is this repeated addition, repeated matrix powers. And again, because Julia is clever, if I have some matrix A equals rand, this isn't one of these matrices, but I could go A times A times A. Geez, keys are failing me now. Blah, 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 blah. Whatever, or I could go A to the 3. Hopefully that gives me the same answer. And it will be faster at doing this matrix power stuff. Won't be doing repeated multiplications. There's a clever algorithm underneath for doing this stuff. So a way of getting the stationary distribution is just repeatedly applying matrix powers. That's that method. Okay, let's go. So where do we go? I'm jumping around out of order, out of sequence. So that's method 2. Okay, so this guy has a special name that I'm going to get wrong. That's called the Frobenius-Perron theorem, I think. Let's see if that's right. It is right. So I talked about Frobenius norm, maybe? Maybe I meant to talk about Frobenius norm. No, I will. I haven't. I haven't, yeah. So this is a special result that you can look at eigenvalues of a square matrix, and you look at this largest one to give you the one. So to give you this, what does it say? We'll make sure we get the words right. So theory of non-negative matrices implies there's a real eigenvalue equal to 1. This eigenvalue with maximum magnitude among all eigenvalues of P. The vector P is proportional to the eigenvalue associated with this maximal eigenvalue. So this is a cool result. So who's happy with eigenvalues? All of you are happy. So if you're not, just because I think it's important, you know, AX equals. So for a given matrix, there's some special vectors that if you multiply by the vector, all they do is change in length. That's what it means. That's how I think about eigenvalues, that an eigenvalue problem is AX equals lambda X. So they've shrunk or grown. That's special, they form a basis, blah, blah, blah. You can do a million things on that. You have special, because they're so useful. So another one that's, we were talking about differential equations and Fourier transforms. If you take a Fourier transform of a second order differential equation, then natural frequencies, the eigenvalues are. It's really useful all through science. Like this will come back again and again and again. This formula AX equals lambda X should look a lot like the stationary distribution. So you've got some probability thing times a vector equals itself. Like if you apply this thing to itself, it's a stationary distribution, it won't change. It's gone to this limiting thing. So that looks like an eigenvalue problem straight away. There's a magic result coming if you want to go and look up Y. If you can go look up Perron Frobenius theorem. To not understand why this is true, but basically the biggest eigenvalue, they're bounded, it's between 0 and 1 for these types of matrices. The number one is the one that gives you it's proportional to the stationary distribution. So it won't be normalized when it comes out. So you'll have to get the eigenvector corresponding to the largest eigenvalue. Its value should equal 1 unless something's gone really wrong. And when you normalize it, it should be the same as this distribution. That's method 3. It's a little bit weird, but it's this cool application of linear algebra to these sorts of problems. Intuition is just basically like I'm applying, this stationary distribution thing here. I keep repeated applying of this matrix to itself. I get the same thing back. It looks like an eigenvalue problem. Turns out the one with the number 1 is the one you care about, which would make sense if you just looked at that equation, It's like AX equals X, like value equals 1. And there's a cool result that the 1 is the biggest one as well. So it's easier than having to find the one that's closest to 1. That's number 3. So hopefully it's like 2 lines of Julia. It's like, just take an eigen, you have to use linear algebra, that's it in the question. So finding the eigenvector corresponding to the eigenvalue of maximum magnitude, normalize and get the approximation. Yes, that should be what it is without having actually done the question. I think number 1 is kind of the hardest one to wrap your head around. Solving this with a matrix solve. So I haven't talked about the linear algebra stuff yet. We'll do that tomorrow. But you want to solve this with a matrix solve. So let's see if I get this right. I get the shapes wrong. If you have something like A is a matrix times B equals X, naively you could go inv A times B equals inv A times X. If A was invertible and if this was a good idea with floating point errors and all these things, don't do this. You have access to this backslash operator in Julia. This is, I'll talk about this tomorrow. This is like high point of human achievement. It's hard to understand how amazing this operator is and everything that goes on underneath they call it a poly algorithm. It's actually incredibly complicated underneath depending on the types of matrices involved. Talk about it tomorrow. The idea is that it will do special things depending on the type. There's a bunch of numerical methods you want to use for linear algebra, and it will pretty much automatically choose the best one. If it's uniquely determined, it will solve it. If it's overdetermined, it will solve it in the least squares sense. So that's probably not what you want. We'll talk about that tomorrow too. Yeah, so, and it all depends on the structure of A. So if you're solving normal equations, again, we'll talk about it tomorrow, blah, blah, blah. The funny thing is that directly this guy, if you just did I minus P, so you try and take it over and solve, you can't invert this guy, it's singular. But you have this constraint that all these probabilities have to sum to 1. So what that actually means is if you calculate this identity minus P, sorry, you just go, sorry. This is called a special thing called uniform scaling. This will make an identity matrix for you. So it's the identity matrix of a particular size. So if you go, you know, what if, just in terms of components, if it's not obvious, or one. 0, 0, 1. You know, that's an identity matrix. You multiply that by itself. So if you're going this minus p and try and invert it, it won't actually work. So you can't solve this directly, but you have a constraint. So I think Yoni sent a link to his textbook. There's a way of like how you'd set this problem up for a small problem where you can just bump one of the rows and substitute in this constraint. So what this constraint would look like. So if we're thinking this isn't a stochastic matrix, but I'm just going to do it anyway. Just pretend P was that. If we're going to go this guy minus P, you know, we subtract off I minus P. What we can do is we only need, like, we can get rid of one of the rows and replace it with the constraint. So this guy should all equal zeros. If you're setting up the matrix problem, like the target of this thing would be something like equals 0, 0, 0. But you might want to add a row on the bottom that's something like 1. So when you substitute in, you have like 1 times p times pi 1. You just want this constraint in. So you're going to have a bunch of coefficients adding up to these probabilities. 1 times this plus 1 times this plus 1 times this equals 1. That's the last row in your answer. There's a link to Yoni's textbook that gives you a hint about how to set this up. The trick will be you have to change this for 1 to L. If you didn't do this, if you didn't bump one of these rows, it will be overdetermined and you might get something weird. Not sure. I haven't tried it myself. See what happens. Okay. Question 4. Any questions on question 4 before I move on? That's the methods, basically. Hand wavy version of it. Okay, cool. So, okay, I think for this one, we can have a look at what RK4 would look like. So, function Euler. So we take a function and we take an initial value and we've got a t. And we're going, okay, y equals 0, length t. F of y1 equals y0. We're going to iterate through. So the t is the same. And we want to basically construct this guy. So this bit looks the same. It's just there's all these prefactors. So h on 6, so h is the t in my example. There's a bunch of factors you want to take a weighted average of. So the first one's easy. Let's see if we can get them on the same page. Okay, so function RK4, we have the same y0 t. We can copy paste a little bit. Okay, so we want to do K1, super simple, K1 equals F of y, t, I. Easy. K2 is you want to take at some intermediate step. So you want to take it with K1. So you need to have calculated K1 to do K2. So it's going to be, oh, I think this is a bit awkward. Okay. I see U is Y. Yeah, so F. I think the brackets are wrong there. 2K2. I'm not happy with that, am I? I'll come back to that, I think. I'll make sure I've got the notes right here for this guy, but let's go. The notes are correct? Okay, cool, cool, cool. Yeah, so t plus h on 2, y, okay, that's cool. Okay. That's not what we want. Okay. So K2 equals f yi plus dt times k1 on 2 and ti plus dt on 2. So it should just be like this going through, etc., etc., etc. And that won't work. Then when we go to do the final one, we're going to go, it looks like the Euler step is we're going to go, you have to do something for K3. Leave that for you guys. And then the final one is going to be something like, we do this weighted average where we're going to go y I plus 1 equals yi plus 1 on 6 times dt times k1 plus 2 times k2 plus 2 times k3 plus k4. Okay, so exercise left for you guys to fill in those ones. But basically, you just want to fill in these intermediate terms. Following through, it's easier for you guys because it doesn't depend on t. The equations of motion, this one are pretty simple. They just depend on the state. They don't depend on t. That's a good picture of this weighted averaging stuff here. So you use some intermediate points and some other ones, take a weighted average, will give you the best version of the derivative. So that's kind of what it will look like. It's kind of straightforward, as long as you're not having a brain fart in a lecture. And it should be just return y. Make sure I got the details right, but it's kind of hard for me to think on my feet. So that's basically it. And Leapfrog will look almost the same again. They're really quite, it looks harder than it is. It'll look kind of terrifying when you go to it. You want to do RK4 and Eulers Method. So for RK4 and Eulers Method, you use the system of first order ODEs. So there'll be, it will be a 4 vector and we'll return a 4 vector. When you do this guy, you'll take an initial value for velocity and position, and it's just this state keeps updating. It's pretty straightforward. A lot of the stuff in there is just for your edification, I'm sorry. So that's kind of the way you do it. So intermediate step for velocity, update the position, use the position update to do the velocity. In terms of the actual questions, yeah, have a think about how you present these results and what you're trying to show. So the real thing is this thing we were talking about before, that if you're trying to go fast, you want the steps to be really big. So the one that will win is the one where you can get away with the biggest steps with minimal error. It's kind of hard because you don't have an analytic one to compare to. All you can compare to is the thing you think will be the best with the smallest time step often for comparison. This thing, this behavior you see of this decaying stuff, you see the energy plot will go away. Has anyone got it implemented yet? Got one guy. Any qualitative features? Anything interesting going on? Yep. Have you seen a difference between, have you managed to get the Leapfrog one to work? Yeah. Anything different between those two? Or yeah. Look for this like in energy. Like it's particularly if you change the time ranges. The thing I'd be looking for is like, if I ran it for a really long time, which one's going to be better? Yeah. So in terms of like targeting, what you're going to want on the answers, like think about if you're going to run it for a really long time, which one would you pick? If you're going to run it for a short time, which one would you pick? And the last bit's just basically hooking into differential equations. So this is really similar to what's going on in the notes. We've got a simple second order differential equation in here. So this is set up as a matrix. So this function is just a matrix in this one because it's linear. So it's easy to do f. Otherwise, you'd have a function of the two states. This is what the API for differential equations looks like. You have a left-hand side that you set up. So you set up this function, same as we were talking about for Euler and RK4. This is the function you pass in. It's a function of x, a mat and t, and it's just this A matrix times x. You pass in this function, you pass in an initial thing. This one, they pass in a time range and optional argument a, because it's this. That's how you set up the problem. Then you just solve. So this is all done for you. So ideally, you'd be aiming for a similar API for your function to this thing. So you take a function, take a time range, you take an initial value, and you go. This will be clever and adapt time steps. So we should see it. Maybe we'll see it. So it's getting busier down here. So this is like, if you go through this thing, have a look at the plots, see with this data of like, if it's adapting the time steps in a sensible way. Your one, I just do fixed time steps to make your life easy. Cool. Any questions? Apart from any? All right, cool. Last one tomorrow. So tomorrow we'll go through a bit of linear algebra and a bit about sparsity. Cool. All right, good night.